Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole, and I'm from Calgary, Alberta. I have over a decade of experience in the field of mechanical engineering in building science, directing the construction of plumbing, heating, ventilation, and air conditioning systems in various high-rise, multifamily residential, and commercial buildings across Western Canada. I love reading about engineering failure case studies. Not just the science behind what went wrong, but what we can learn as an engineering community to prevent future failures from happening. Starting a podcast has been a dream of mine for a long time, and I want to thank each and every one of you for listening. I hope these stories interest you as much as they interest me. Check out the link in the show notes of this episode to see photos from this week, and please rate, review, and subscribe to the podcast so more people can find it. This week in engineering news, a Princeton University study reveals how microplastics carry long distances through soil, sediment, and other porous material. The research team was led by Sujit Datta, an assistant professor of chemical and biological engineering at Princeton. The purpose of the study was to predict the amount and location of plastic contamination by studying how water moves through contaminated mediums. The research team made the media transparent to track particle movement in real time. It was previously thought that particles, once stuck, would remain there. However, during the study, they found that while microplastic particles became stuck in clusters when traveling through porous material, as fluid pressure increased, those particles broke free and moved substantially further. This occurred in a cyclical fashion. Get stuck, break free, get stuck, break free, and so on. Two types of particles were tested, sticky and non-sticky. The researchers found that the movement process was the same, although non-sticky particles tended to collect at narrow passages, whereas sticky particles could become stuck at any surface. The information gained from this study can help inform models to better understand particle movement and the impact on vulnerable areas, such as farmland, rivers, and aquifers. It can also assist with deployment of engineered nanoparticles to remediate contaminated areas. Check out the link in the show notes for this episode if you want to read more on the study. Now on to this week's engineering failure. The Hyatt Regency Walkway collapsed in Kansas City, Missouri in 1981. Construction of the 45-story hotel began in May 1978 and was completed in July 1980. It costs roughly $150 million to build, which is equivalent to almost $475 million today. The Hyatt Regency Kansas City is part of the Crown Center complex and was built by Hallmark Cards, who still owns the building today. Yes, the same Hallmark who makes greeting cards. There were many delays during construction, including collapse of a 250 square meter section of the atrium roof. The main lobby, a defining feature, contained three 36-meter-long suspended walkways to connect the hotel tower to the conference and function area on the opposite side of the lobby. The second and fourth floor walkways were stacked on top of each other, and the third floor walkway was offset from the other two and independently suspended. On July 17, 1981, at 7:05 p.m., during a tea dance in the atrium lobby with approximately 1,600 people in attendance, the second and fourth floor walkways collapsed, crashing to the floor below. The structural design was completed by Gillum Colasso Inc. out of St. Louis, Missouri. Jack D. Gillum was the engineer of record, with Daniel M. Duncan as the project engineer. What does this mean, you ask? Gillum's engineering stamp was on the structural blueprints. He was the legal engineer of record. But Duncan completed the structural engineering work and managed the day-to-day design tasks. It's fairly common for the owner or partner in an engineering firm to oversee and stamp major designs, while engineering staff complete the design tasks. Although there is usually significantly more oversight than what occurred here, but more on that later. The main structure of each walkway consisted of two box beams running the length of the walkway. The box beams were made from two C-channels welded together lengthwise to create a box shape, giving them the name box beam. Cross bracing between the box beams with Q-deck laid on top and a layer of concrete, created the walking surface. Each walkway weighed roughly 8,500 kilograms. All 3 walkways were suspended from the atrium roof structure by hanger rods. Because the 4th and 2nd floor walkways were stacked, the original design intent was to hang them from the same set of 6 rods suspended from above. The original design meant that one set of rods would support both walkways, commonly referred to as a single rod system. Notice I said original design intent. The single rod system is not what was built on site. The connection details to support the walkway included the hanger rod passing through the box beam with a threaded nut on the underside of the beam. There are 3 types of connections: simple, complex, and special. Simple connections have no unusual loads or forces applied to them and can be designed using the American Institute of Steel Construction Manual. As I understand it, these are standard details that can be reused within the manual parameters without requiring specific calculations. Complex connections have extreme or unusual loads or loads from several directions and require engineering to design. Special connections are a hybrid of both. When a simple connection has a concentrated load and/or the manual of steel construction can no longer provide all of the necessary info to design, it becomes a special connection and requires engineering. There are also redundant and non-redundant connections. If, when a connection fails, it would not result in a failure of the structure because there are other connections available to carry those loads, it is considered a redundant connection. But if when a connection fails, the structure collapses, that connection is non-redundant. The box beam hanger rod threaded nut connections at each walkway were considered to be both special and non-redundant connections. As I said earlier, during construction, the design was changed. The contractor, Haven Steel Company, had argued that if they used a single rod system with one set of rods to support both walkways, the rods would be damaged when the 4th floor walkway was hoisted into place. Which I have to admit seems to be a reasonable concern. You'd have to lift the 4th floor walkway into place very carefully in order to protect the rods. And what is plan B if you took all possible precautions and the rods were still damaged? The design change during construction resulted in 2 sets of rods, or a double rod system. Engineers don't like to get caught up in complicated names for things. Single rod systems have 1 rod, double rod systems have 2 rods. Easy peasy. The double rod system resulted in 1 set of 6 upper rods from the structure to the 4th floor walkway, and then a second set of 6 separate lower rods hung from the 4th floor to support the 2nd floor walkway below. The upper and lower rods through the 4th floor beams were offset by 100 millimeters. In the original design scenario with a single rod system for both walkways, let's consider the load applied to each walkway connection detail to be X. However, in the redesign scenario, which is what was installed, where the 2nd floor walkway was hung from the 4th floor, or a double rod system, the load applied to the 4th floor walkway beams was now 2 times X. The double rod system doubled the load on the connection details at the 4th floor beams. This would have been fine, except the connection details were not re-engineered or even checked when the hanging method was revised to a double rod system. Not the beams, not the rods, not the threaded nuts. Not even when Haven Steel submitted shop drawings of the walkway and connection details to Gillum Colliso for review, which they approved. To recap, the design was revised to a double rod system during construction, which then doubled the load applied to the 4th floor walkway. The connection details were not revised or even checked during design or construction. But wait, there's more, because it's never just one thing. Remember the box beams running lengthwise under each walkway that were constructed from 2 C-channels welded together to create a box? Well, the welded seam meant that of the 4 sides of the box beam, 2 of the opposite sides would have welded seams, and the other 2 sides would be solid steel. Rather than running the hanger rods through the solid sides, they ran through welded sides. This is the weakest part of the beam. And this wasn't just the case on the 2nd and 4th floor walkways. All 3 walkways were built like this. I'm no structural engineer, but even I can see that this was a really, really bad idea. The welds were originally intended to be on the sides of the beams, but since Gillum Colliso did not complete adequate field reviews of the walkways during construction, the beam orientation was not caught or corrected. Following analysis of the failure, the welded seam on the bottom of the 4th floor beam split, causing the threaded nuts to slip through the gap and the walkway to drop several inches. Then the upper seam of the beams failed as well, causing the 4th floor walkway to fall, and since the 2nd floor walkway was hung from it, They both collapsed onto the floor below. Further analysis following the collapse suggested that the east line of hanger rods failed first, although it was determined that a failure was inevitable. Had the support detail not changed and one set of upper rods supported both walkways, then the third floor walkway would have actually been the one with the highest probability of failure, as it was wider and could fit more people while having similar design flaws with respect to the box beam construction. In short, all of the walkways were under-designed. The calculated maximum loads acting on the connection details, as required by the Kansas City Building Code, were 181 kilonewtons at the fourth floor walkway and 90 kilonewtons at the second floor walkway. Notice that the fourth floor load is double the second floor load. The loads on the fourth and second floor walkways at the time of failure were estimated to be 95 and 51 kilonewtons respectively, roughly 50% of what was required. The connection details did not meet the Kansas City Building Code or the American Institute of Steel construction requirements. Any of the fourth floor connections were candidates for failure, and with little capacity rating in each, collapse was imminent. The walkways were so under-designed that they could barely support themselves, let alone any additional weight. It's surprising they hung for a full year before collapse, and it's too bad they hadn't collapsed under their own weight when no one was in the atrium. But unfortunately, that wasn't the case. At the time of the collapse, it was believed there were 40 people on the second floor walkway and 16 to 20 people on the fourth. When the walkways collapsed on July 17, 1981, 114 people were killed and over 200 were injured. The collapse is still the deadliest non-deliberate structural failure in U.S. history, and it's the deadliest structural disaster until the collapse of the North and South World Trade Center towers on September 11, 2001. Volunteers quickly responded to the plea from the rescue teams and brought jacks, cranes, ropes, and saws to assist in the rescue mission. To mitigate the risk of fire, the power was cut, which impacted rescue operations. The main floor exhibition area was used as a temporary morgue, and the lawn and driveway acted as a makeshift triage. The last person was rescued at 4:30 a.m. following removal of walkway spans by heavy crane. Mark Williams had spent more than 9 hours trapped. He had dislocated legs and almost drowned by water from the sprinkler piping that burst when the walkways collapsed. He was very lucky to survive the collapse, but so many others were not as lucky. An investigation into the cause of the collapse reported the following findings. Following the atrium roof collapse during hotel construction, Gillum Colasso was given an additional fee to recheck the structural design. Gillum himself assured the owners that he would personally look at every connection in the hotel. But he didn't. He only checked the atrium roof steel, not the walkways. The steel fabricator, Haven Steel Company, had an in-house structural engineer that could have designed the connection details, had the drawings specified that they were to do so. But the drawing stated that the structural connection details were designed by the engineer and that design by the fabricator was not required. Special welds, stiffeners, and bearing plates, as well as high-strength steel hanger rods were required but not specified by the structural engineer. The investigation did not find the necessary tests and calculations in Duncan's records which would have shown that he had verified his connection detail design for a double rod system. It also found that Duncan did not adequately review the shop drawing sent by Haven Steel, nor did he review the connection detail in relation to the design specifications of the Kansas City Building Code or the project contract documents. Duncan argued during proceedings that his intention was for the fabricator to complete the calculations and therefore assumed that they had done so before the shop drawings were submitted. What he intended is not really relevant here, only what was specified on the contract documents, which the investigation found had clearly stated the connection details were designed by the engineer, not the fabricator. Drawings and specifications have to be clear to avoid any conflict. And lastly, the investigators found that neither workmanship nor materials played a significant part in the failure. This meant that there was no one else to blame but the design and the people who were responsible for that design. In the aftermath of the disaster, the structural engineers were found culpable of gross negligence, misconduct, and unprofessional conduct in the practice of engineering. There were 3 main parties that received disciplinary action. The engineer of record, Jack D. Gillum, the chief project engineer, Daniel M. Duncan, and the engineering firm Gillum Colasso Inc. lost their licenses to practice in Missouri, Kansas, and Texas, and their membership with the American Society of Civil Engineers. They appealed this ruling, but it was ultimately upheld. Duncan was an engineer himself, and while he did not stamp the drawings, he was the project engineer and in charge of the design. The review commission found him guilty of gross negligence in preparation of the structural drawings and failure to properly review the steel and erection shop drawings. Although Duncan did not stamp the drawings, as an engineer himself, he had an obligation to public safety. He should have known better. As the engineer of record, it was Jack D. Gillam's stamp on the structural plans. Gillam was found liable and responsible for the acts and omissions of Duncan, and Gillam was also negligent in failing to review or assure someone had reviewed the drawings before he stamped them. He also failed to review the installation on site, even after requested by the architect. And lastly, Gillam Colosso Inc. was found liable and responsible for the acts and omissions of Duncan and Gillam. So what can we learn from this failure? Drawings or contract documents must be clear. Always double-check the details of critical components to your design. Even if they're designed by someone else, a second set of eyes can save a lot of people. And lastly, engineers must review their design on site during construction. The beam orientation could have been caught and corrected during construction, but it wasn't. Today, the lobby remains the same original layout and design, although the walkways were never rebuilt. The hotel was renamed the Hyatt Regency Crown Center in 1987, but has been called the Sheraton Kansas City Hotel at Crown Center since December 1, 2011. A memorial for the victims was built in 2015 in Hospital Hill Park across the street from the hotel. It was dedicated on November 12th of that year by the Skywalk Memorial Foundation, which is a nonprofit organization created for victims of the collapse. This included a $25,000 donation from Hallmark Cards. Check out the podcast page, link in show notes, for photos from this week's episode. And if you want to chat with me, my Twitter handle is @failurology. Thanks everyone for listening. If you're enjoying what you're hearing, please rate, review, and subscribe to the podcast so more people can find it. And don't forget to tune in next week to hear about the Grenfell Tower fire. It's a really sad story and it's still ongoing, but the fire uncovered a way bigger problem and started a long overdue conversation about the combustibility of building materials. But more on that next week. Bye everyone. Talk soon.